Okay, so today we will cover this convolution neural network. So, and we will we will see one of the project where we can use this convolution neural network. And again, I am going to show you how that Google ImageNet is trained and how we can use that pre-trained model to classify the fruits and how we can make a use of that, how we can make a use of pre-trained model provided by the Google, which is trained on 1,000 different classes. Okay, so we will just demonstrate with that. So this is what the it's obviously an advanced version of neural network. So this is the basic architecture for the uh, convolution CNN or convolution neural network. It is also called as conveyed. So now this 32 by 32 pixel image we pass to the convolution layer. Okay, so the first layer is nothing but a convolution layer. Then we just partition or we just take a features out of it and we pass it to the ReLU activation function layer, and then the output for the ReLU layer is passed on to pooling layer, and this pooling layer is maybe optional layer. Suppose the image is bigger size, then we have to just reduce the dimensions. In that case we use this pooling layer, and this three chains we can repeat anytime or multiple times till we satisfied with the good results, like convolution, then the ReLU pooling, or you can say the max pooling, convolution, the ReLU max pooling. And then once we get the features out of it, we attach a fully connected layer, which is nothing but a normal or neural network. Okay, so over here, and then that neural network we pass it to I mean that last layer, that is nothing but a classes what we have seen yesterday. Okay, so this is the basic structure in the CNN. So if you observe here, if we pass this car image to the to our CNN, then how we can predict whether it is a car, or how it gives the probability over here. Okay, so first layer is the convolution layer. So it initially it finds the basic features out of it, like whether it is a sharpen and the small curve. Okay, and then this ReLU layer, I mean the output of this convolution, pass it to ReLU. Likewise, so it find out the features out of it. Okay, and we pass, I mean the last layer is nothing but a fully connected layer, which decides the past image is from which particular class. It depends upon the probability. So last layer is nothing but our I mean softmax function or softmax layer. So we'll first see uh, what is inside the convolution layer. So when we pass the image to the convolution layer, uh, we generally perform some operation over here. So this is the image, which is nothing but 5 by 5, and this kernel we consider as 3 by 3. We just we just move this kernel over the image. Okay, slide, and after that we'll get a activation map. Okay, so that kernel, initially the values for the kernels are nothing but a it again a part of the image itself. Okay, and it find out the basic features out of it, and we are just multiplying, or it's a dot product between this image and this kernel. So how it look like? So it gives the activation map so in short, we are finding some feature map over here from the input image within the convolution layer.
Mm-hmm.
So what is the convolution learning? So we are learning a small features from the particular image. So like a curve, and then very small features in a first convolution layer. So this is the famous diagram, and this is the diagram from a particular source I have taken. These are the feature, or you can say the feature lookalikes when in a first layer of the CNN feature map we can see.
Okay.
And then we use this ReLU activation function. So whatever learn feature, we pass it to this ReLU function, which gives you obviously the results between a value and zero. So max value and zero. So it helps to add a non-linearities within this.
Mm-hmm.
And then we pass the ReLU output, ReLU activation function or layer output to the max pooling layer, which generally downsample our image. Okay, so how it look? So we generally take max pool with 2 by 2 filter. So we consider the maximum value within this. So
Yeah.
in this, 3 is max, like this. Okay, so this is the working within the max pooling layer. And then that whatever output we get in the pooling, we pass it to the fully connected layer. Okay, so this uses the high level features detected by the convolutional and pooling layers to classify the input image into classes defined in the training set. So and finally the last layer contains the softmax function, which decide the particular input image is from which class, depending upon the probabilities. Okay, these are the different architectures we can use, like convolution ReLU pooling, convolution ReLU, convolution ReLU pooling. Finally, fully connected layer. So this is the basic architecture or the way of defining this uh, CNN. This is one of the site where you can actually see some results, how the features are, look likes and everything. So I'll share with you this. This is what the retrained model or uh, provided by the Google. So no need to learn the features again and again. So uh, so if you observe this, these are the layers provided. Okay, and this is the last layer is nothing but our fully connected one. So uh, we can again on a particular data, we no need to train the particular model from scratch. We have to just replace the number of classes uh, within the image. So if I want to train a classifier which classifies the different fruits. Okay,
Mm-hmm.
so I'll just replace the last classes. Okay, for this model, like in my case, if I want to classify the fruits, then the apple, orange, banana, these are my classes. Okay, I'll just change the last one and I'll use the pre-trained model to retrain my data set. Okay, that is what the transfer learning. So you make a use of pre-trained model to train on your data, and this pre-trained model is already trained on thousands classes, thousand different categories, or millions of different images. Okay, So that is what the pretend model provided by the Google. Okay, I will just look into the code.
Okay.
So same data set we will consider over here for understanding. So now this is the flow chart behind the CNN while uh, classifying the digits. Okay, so this is the input image, 28 by 28 pixel. We will just pass this image to the convolution layer 1. Okay, and this image is I mean there are which results in 16 new images. One, I mean we apply 16 different filters which are 5 by 5 pixel over this image, and which results in 16 new images. Okay, so we downsample or we apply the you can say the max pull layer on these images, which reduces or decrease the resolution for that images. So it gives us 14 by 14 pixel 16 different images. So the output for the convolution layer 1 is 16 different images for each filter applied on the what this image. Okay, now this output is now pass we pass this output to the convolution layer 1. Okay, so here we apply, and which gives us a 36 images which are learned uh, from this thing, and where we apply 36 different filters. Okay, and which gives us 7 by 7 pixel 36 images. Okay, with by applying the max pooling. Okay, so there are 36 output channels. So there are total 16 by 36, that is 576 filters in the second convolution layer. Okay, and the resulting image are downsampled again to 7 by 7 pixel. Okay, now this 7 by 7 pixel images, 36 images, we will pass to the fully connected layer 1. Okay, and which has 128 features. So if you say 7 by 7 multiplied by 36, so 174. So we have studied that yesterday, that we have to flatten a particular image into a vector, and we pass that vector to the fully connect or the neural network. Okay, so here that vector becomes 174 pixels or the values. Okay, so and the output for that particular fully connected layer is 128. So input is 1764. So we have designed such a neural network which takes input as 1764 and gives output as 128 features. Okay, and then again we apply this 128 features, we pass it to another fully connected layer, and which results in a 10 classes. Okay, so these are the 10 different features which is the output for the second fully connected layer. And at the end we will decide or will pass that uh, 10 features to the softmax layer, and which decide the number depending upon the probability. Okay, so if we see over the probability of this is zero point 0.8, and that is nothing but 7. So this decides the class for this particular past image. Okay, So this is what the flow chart or the flow of the CNN. Okay. So here we will take that MNIST data set. So we have to just
Yep. I think this we have seen yesterday. No, we import all these libraries and the data
yeah
also.
yeah
We have seen. I can go down. You can directly
extract
maybe jump to
yeah
the place where we start actual
training yeah.
what is the training and
Okay,
how are
so
you basically designing that convolution network.
okay, so some parameters are needed like learning rate. So this decide how fast or slow we will learn the uh, weights. Okay,
Yeah. Yeah.
train and training iteration, number of training iteration.
Mm-hmm.
Then batch size for the data we have converted. Display step. So these are the hyperparameters, and the input is obviously 784. Classes at the end will get 10. Okay. Now this placeholders for storing x and y. Okay, over here, and these are the weights.
So you
We
decide
have done
random weights, is it?
initially, yeah.
Okay, yeah. No, I am sorry. Kernels, I wanted to know. Sorry. Yeah, weights, I know, I know.
Okay, so weights are randomly designed, and then
Yeah.
biases. This is the structure we are going to follow. So initially, the 5 by 5 convolution uh, for 32 different. So initially, we'll pass the uh, 28 by 28 pixel image to this conversion layer, which where we apply 32 different filters of 5 by 5 pixel. Okay, and then the results or the output goes to ReLU, then max pooling, and then again this convolution which has 64 different filters of 5 by 5, then the ReLU max pooling finally will go to the fully connected layer. Okay, so
I will
TensorFlow.
directly see the code then.
Okay,
Because,
sure.
yeah, instead of. Because just want to know how are we deciding or designing these kernels?
Again, here it it is just what we can say, the practice we apply. So no need to. There's no mathematics to calculate the size of the kernel.
Hmm. No,
So
but
mhm.
where are we saying that how many filters have you used?
In this, I'll show
Hmm.
you. So this is the reshaping the particular image into 28 by 28 pixel. Okay, and this is the first convolution layer. So x multiple, that is wx, and we will add the b over here, that is what the bias. Okay, and we say strides. So in strides, this first parameter is always one, first and last always one. So this last says the channel, whether it is one gray. So currently it is a grayscale image, so we are considering one. Okay, and this one for image number, and this is the y value, and this is the x value for that stride. So it is always one by one. Okay, and then padding is same. So when we say same, that means we consider zero padding. Okay, and then we just add. So this is what the wx we implemented. Then we add the bias over here. Okay, after adding the bias, uh, so this output goes to ReLU over here, and uh, this is the output for the ReLU function, that is convol one. So if you observe the structure, so input image is like 28 by 28 grayscale, which gives output like after ReLU like 28 by 28, 32 different.
But where did we say that we have 32 filters, Nilesh?
Yeah, yeah.
I'm trying to figure out that only. Where is that number 32 coming from?
So 32, just wait. the size of the image is like
Sorry?
uh, so here it is getting that like the size of the here if we check the shape of this list, then it becomes
That I
30.
understood. My
Uh,
question is,
mhm.
how is that it is coming down to 32? You are
So
printing that shape. I understood that.
yeah, so here we are
In the code,
mhm. So here
the
we are
your
saying
weight itself is the kernels, is it?
yeah. So here we are generating it like 5 by 5, one channel and 32 different
Because your weight itself is the kernels then.
filter. Yeah.
Okay. Okay.
Similarly, we just apply this for downsampling. We just apply this max pooling layer over here, okay. So which has 2 by 2 and one stride, okay.
Okay.
And this convolution fully connected layer, and which returns this out value. Okay.
Okay.
So this is the new the CNN which we have. So this drill down to 1024 and then 1024 to 10 classes, 10 different classes.
Okay.
And similar to that neural network, we find out the cost. So which where we apply the cross entropy with logics. And so this spread is nothing but a graph which we have built over here using this function spread. We pass it to this and the labels, okay, which defines a cost. And using this RMS prop optimizer, we can just minimize this uh, cost with the help of learning rate, and which becomes a optimizer, okay. And here we find out the correct prediction. So from this predicted as well as the actual y, okay. And this is what the correct prediction. And here we find out the accuracy. So this corrected value which reduces to the we convert it into zeros and one, which reduces to the accuracy. Now we'll
Okay.
see how we can build within a session. So here we are initializing the all the variables, and this is what the learning. So while step multiplied by the batch size, these are the training iteration. We take a data from this in a batches. So X and Y, instead of taking single image, we take a batch of image and we pass it to the uh, feed it to the optimizer, okay. So this session dot run optimizer feed X and Y, okay. And then we print the status of every 200 iteration over here. So at iteration 20,000, the loss is 248 and the accuracy is like this 96%. So so this is what the training g- and the loss is now at this iteration, the loss is now this 17 and the accuracy is around 99%. So if you compare the accuracy between the neural network and this, uh, obviously the CNN gives you the good accuracy.